Hello class, this is Mr. Hart, and in this podcast we want to start our unit on forces. And up to this point we've been looking a lot at motion and how we describe motion, but now we want to talk about what actually causes those motions, and forces is a big part of that. Okay? But before we get into what force actually is, let's talk about some terms that we need to know that help us describe forces. Okay? So these two terms are things that you'll see a lot in physics. A lot of the quantities that we try and describe are described by either being a scalar or a vector. Okay, so a scalar is a physical quantity represented by a single value, whereas a vector is a physical quantity represented by a value and a direction. Okay, so there's scalars and vectors in physics. Some examples of scalars are like distance and speed. Okay, when I need to tell someone how far away something is, I only have to give them a single number. Oh, that object's 10 meters away, or that city's 20 miles away, whatever it is, right? I just have to give them a value. I don't have to specify any directions. Likewise with speed. If you tell someone how fast you were driving, you only tell them I was going 25 miles per hour or 35 miles per hour. You don't have to specify that you were traveling north or you were traveling west, right? You just have to give them single values. Directions aren't important in those cases, okay? Whereas with a vector quantity, you do have to specify direction. Okay, velocity is an example of a vector because we specified whether it was traveling to the left or traveling to the right. Okay, and so we have to be specific in specifying the direction and the value for these quantities. Okay, so the reason I bring this up now is we've been dealing with a lot of scalars, some vectors, but force is a vector. Okay, so keep that in mind. It's important when you're looking at force to look at the direction, okay? Because a person pushing on you in this direction is different than a person pushing on you in that direction, right? Forces are going to add and cancel based on direction. So keep that in mind. Force is a vector. Now, with that being said, let's look at what a force actually is. So let's answer the question, what is a force? Now, you may have a pretty intuitive sense of what a force is, okay? You've probably been pushed before. You've probably been punched before, okay? You've hit into something, okay? You can feel a force, right? You're very, familiar with how a force feels. It hurts a lot of times, right? But we want to be very specific with physics and how we describe forces. Now, some people may want to say, well, it's the ability to make something move, okay? And that's kind of the definition we want to use. But keep in mind, just because you apply a force to something doesn't mean it's going to move, right? Just because you push on a wall doesn't mean that it's going to tip over or move, right? So we're going to use kind of a vague definition that a force is the influence which tends to change the motion of an object, okay? This idea that a force can make something move, but it doesn't necessarily. So just keep that kind of in the back of your mind, that just because there's a force doesn't mean there's a movement, but it does have a tendency to change the motion of an object, okay? In a little bit, we'll be very specific with how we actually define it mathematically, but this is just kind of the idea for now, is it's this thing that we can apply to change the motions of the objects. Okay? And again, it's very important to remember that forces are vectors. Okay? They are dependent on direction. Okay? And then forces, last of all, are measured in newtons in physics. That's their SI, which we represent with a capital N. And if you remember going back to the unit's reference sheet, a newton is defined as a kilogram meter per second squared. Okay, so basically those are equal. A newton is a kilogram meter per second squared. So if you ever see these units, you can write it as a newton. If you ever see a newton, you can write it as these units. They're interchangeable. Okay, but if you see newtons, that's the unit of force. These are the units that it's equal to. Okay. All right, so let's look at some forces that you probably are familiar with, okay? Let's just look at a simple example of someone pushing a shopping cart. Let's just try to identify some forces that would be present, okay? Well, first of all, the obvious force is the guy pushing on the cart. He's going to be trying to push the cart in that direction, okay? So there's going to be a force that he's applying to the shopping cart, okay? He's going to be pushing on the floor to help him walk, okay? The shopping cart itself is going to have a gravitational force on it, okay? The man's going to have a gravitational force on him, okay? And you can already see that this is really getting ugly to diagram, okay? There's a force on the wheels and so forth. So we want to be very particular with how we draw these diagrams. Otherwise, they're just going to get ugly really fast, okay? And so one of the things we like to do is we like to use what we call net force, okay? And so the idea of net force is the total force acting in each direction. So instead of having to draw every single arrow on a force diagram, we just look at individual arrows, okay, and just draw them from one direction. Okay, so we're going to draw all the forces on the left side. We're going to draw all the forces on the right side, okay, all the forces going down and all the forces going up, okay. And so instead of drawing them at all different locations, we kind of draw them from a single point, okay. So that's one thing we do. And then we kind of combine forces and call them net force, okay. And so another big idea is that if all the net forces are equal, or basically they are equal to 0, okay, all the stuff pushing on the left is equal to all the stuff pushing on the right, all the stuff pushing up is the same as the stuff pushing down, okay, that means we have equilibrium, okay. So that's another key word you want to know, okay. So something is in equilibrium if all the forces are balanced, okay, or equal to 0, okay. So let's look at an example of this so we can get an idea. So let's say we have these people playing tug of war, okay, and we could draw individually and say, okay, well, this person's got a force going that direction, or sorry, they have a force going that direction pulling that way, this person's got a force pulling that way, this person's got a force pulling that way, okay, there's forces of them pushing on the floor and that type of thing, but we can kind of draw it from the center, okay, and say, okay, let's look at all the forces and just draw them from this point. So there's a force going that way from the first person pulling. There's a force going that way from the second person pulling. There's a force going that way from this person pulling. And there's a force going that way from this person pulling. Okay? So we draw it from the center. That makes it a little bit easier. And then we can compare. If all the forces on this side are equal to all the forces on that side, then the net force is 0. Okay? And if the net force is 0, then this object is in equilibrium. Okay? And so in this case, it's not going to move because it's in equilibrium. All the forces are balanced. Okay? All right, we'll get to more of that in just a second. But let's continue describing what force actually is and what it can do. Okay? So what are the different things that a force can do? Well, it can obviously make objects move, but we can think about it more particular. Okay? It can speed up an object. Okay? For example, someone kicking a soccer ball will obviously apply a force to the soccer ball and make the soccer ball speed up. It can slow down an object, okay? A truck applying its brakes it's gonna slow down the truck, okay? So it can cause a deceleration or an acceleration in the negative direction, however you want to think about it, okay? It can change the direction of an object, okay? Like a tackle in football obviously applies a force to change someone's direction. It can rotate an object, like a bolt or a washer or whatever it is, okay? You use a wrench to rotate that object, you apply a force. Or it can change its shape, okay? So that's the 5 things that forces can do. And if you think about it, anytime one of those things are happening, there's some force that is being applied. Alrighty, let's keep going. I know there's a lot of terms that we're describing right now, but we want to make sure we have a good understanding of what force actually is, okay? So next, let's look at what types of forces there are, okay? What are the different types of force, where they come from, how are they applied, okay? So the first and biggest force probably to be aware of is gravitational force. Okay, so gravity obviously is the force that pulls anything towards the earth. This is why you can't just jump and start flying away into the sky, right? There's a force that is bringing you back down. Okay, gravitational force, a very common force. Hopefully you're already pretty familiar with it. Okay, there's also what we call the normal force. Okay, and the normal force is the force an object exerts that is perpendicular to the surface. Okay. And so what that means is, for example, when you rest a book on the table, it's got 2 forces that keep it in equilibrium. The gravitational force, or its weight bringing it down, and the normal force of the table pushing up on it, okay? And so those 2 forces balance, right? They cancel out, they're in equilibrium, and that's why your book doesn't plow into the table or start flying off into the sky, okay? So the normal force is just kind of this natural force that is applied when any object's being pushed on. Okay, when you push on a wall, it pushes back with a normal force. When you rest something on a table, there's a normal force. When you sit in your chair, okay, there's a normal force. It's why you don't plow into things because of gravitational force. This is the equilibrium, okay, that keeps everything just sitting there basically when it's on a surface, okay. And so the reason it's called the normal force is because in math we have a term for 3 dimensions for perpendicular, and that term is normal. So if something's perpendicular in 3 dimensions, it's called normal. Okay, and so that's what it comes from. It basically just means perpendicular force. Okay, and so that's for any object. If it's pushing on something, it pushes back with a normal force perpendicular to its surface. Okay, and if something can't apply that much normal force, then it will break. Okay, so if you put a book on the table, it's fine. It can apply that normal force. If you put an elephant on the table, it probably will break. Okay, it can't apply that much normal force, so it will plow through the table and break it. Okay, so another force you probably have heard of is friction, and friction is the force caused by resistance to movement across a surface. It also can be caused by air resistance, right? Things not wanting to move, and this is just caused by grooves and bumps in the surfaces of things. Because things aren't perfectly smooth, they're gonna hit into each other a little bit as they drag across the surface. Okay, so anything that is moving across the surface is going to have some type of friction that resists that movement. Okay, so you're probably familiar with this one. Okay, but air resistance, friction, those types of forces. Okay, another force is the applied force. This is the fancy name for hitting something or pushing something. Okay, so when a hammer strikes a nail, that's an applied force. So physicists are very specific. Something like the pushing force wouldn't have been very good or technical for them, so they had to come up with a fancy word, and that's applied force. Okay, but it just means pushing something, hitting something. That's an applied force. Okay, other forces are things like tension. Now, this one's commonly confused. Tension is not the ability to pull on something. This is still applied force if someone's pulling on stuff, right? They're just applying it in this direction. But tension is the actual force in the rope. Okay, so tension is the reason why this rope doesn't rip apart. Okay, these fibers in the rope are holding the rope together. Okay, that force is what we call tension. Okay, and so it's not the pulling of the hands, right? That's the tension. It's the rope itself holding together. That's the tension. Okay, basically the ability of an object not to want to change its shape. Okay. Other forces you'll see are spring and elastic forces. When you compress a spring or you pull on a bungee cord, okay, those types of things are going to be spring and elastic forces. Basically, an object that can change its shape but wants to go back. Okay, so when you compress a string or compress a spring or pull on a spring, it wants to go back to its original shape. That's the spring and elastic forces. Okay. And then the last one that you probably are familiar with is electric and magnetic forces. Okay, if you've ever tried and take two magnets together and try and push them together, you'll notice there's a force. You can feel that, North Pole versus North Pole, right? So there's definitely forces that magnets and electricity can apply. Some students wonder, how can electricity apply a force? How can it make something move? If you've ever used a blender, okay, it's obvious that electricity can cause stuff to move, so electricity can cause movements. Okay, so it can apply a force. Alrighty, so that's all the forces that we want to look at for this class. So when we're looking at identifying what forces are being applied in an object, not only do we want to know what direction they are going, but we want to know how large they are and what type of force they are. Okay, and so the last thing we want to cover is how to actually draw these diagrams of the different types of force, and these diagrams are called free body diagrams. Okay. So a free body diagram is just a diagram of all the forces acting on an object. Okay, and again, we kind of start from a central point to make things easier on ourselves and just kind of look at net force. Okay, but for example, this box right here that's on this ramp, it has a force pulling down from its weight or from gravity. Okay, it's got the normal force pushing out, and it's got a force of friction holding it on the ramp because of the surface. Okay. And so this is an example of a diagram, a free body diagram. Okay, it's just looking at all the forces on an object. Okay, let's try one ourselves. Let's say we have a person driving down the road, okay, and we want to draw their free body diagram. We'll start with just a central point. Okay, again, rather than look at individual forces on the tires and from the engine block and all that thing, we're just going to draw from a single central point. Okay, and look at forces. Well, one of the first forces is that they have the gravitational force on them. Okay, so we're going to have a force of gravity, and I'm going to notate it like this: force sub g, force of gravity. Okay. Also, if this car is on the road, there's going to be a normal force pushing up. Okay? And I will notate that force N, force sub N. Okay? So normal force. Okay? Now, if this car is not plowing into the road or flying into the sky, these two should be balanced. So hopefully we draw those about the same length. Okay? Because it's a balanced force. They're not, again, not plowing in the ground or flying in the sky. So gravity, balance is the normal force. Okay? We also have a force of friction on the car. Okay? And I will notate this with a K in this class because it's called what we call kinetic friction. So you may want to make a note of that. We don't use the letter F, we use a K. So that is force of friction. And if you would be consistent with that, that would be great when you are doing your diagrams, just because we want to be particular. And we'll talk a little bit more about this later, but use a K for friction force for now. Okay? And then this is the tricky one, the force applied. Okay, so the engine block is applying a force on the driver. And the question is this arrow supposed to be the same length, shorter, larger? Okay. Well, it just depends on what the driver's doing. If they're just cruising down the road at the same speed, then they should be in equilibrium. Okay, constant speeds are equilibrium. Okay, so in that case, the applied force should be the same length as the kinetic force, or the force of kinetic friction. Okay, if it's longer, that means they're speeding up, and if it's shorter, it means they're slowing down. Okay. Don't worry too much for right now for how long the arrow should be, but these are the four forces acting on the driver in this case. Okay, the normal force, the gravitational force, the friction force, and the applied force. Okay, so if you were actually drawing this on your paper, you wouldn't have this little diagram right here. Your drawing would just look like this. Okay, the normal force, gravitational force, friction, and the applied force. Okay. All right, let's try one more example. And I want you to think about this example. Okay. So a ball is thrown into the air with no air resistance. What will be the force diagram on the ball while it is in the air? Okay, so someone's throwing a baseball or whatever it is into the air. What is the force diagram? Okay, so let's start by drawing a central point, and then let's think about the forces. Okay. So first of all, there's gravity acting on the baseball. That's what's going to pulls it down. Okay. So there's definitely force of gravity. There wouldn't be a normal force because it's not on any surface. We're assuming there's no air resistance, so there's no friction force. And we're assuming that it's in the air already, so there's no applied force. So this is our diagram right here. That's it. There's just the force of gravity acting on the ball. But if you think about it, that baseball is going to be traveling in this direction. But that's a little weird if you think about it, because there's no force in that direction, which is really strange. You would think that if it's moving in that direction, there should be a force. Okay? So this leads us to a key idea. Okay? And that key idea is that there is not always a force in the direction of movement. Just because an object's moving a certain direction doesn't mean that you need a force to go that direction. Okay? And so just keep that in mind as you're doing your force body diagrams. Just because it's moving in a certain direction doesn't mean there has to be a force in that direction. Okay? But that's it for today. Sorry there was so much to cover, just a lot of terms and concepts that we need to go through. And again, we'll kind of refine these ideas as we go along, but I just wanted to introduce you to how we look at forces and some of the things we want to do. Okay? But your homework for today is just to be able to draw those free body diagrams like we've been practicing. Hopefully that all made sense. Let me know if you have any questions, and thank you for watching.